So one of the major goals of this chapter is to not only understand what a rate law is, but also to derive it experimentally, either doing that in the lab or when provided data that somebody else collected, how do you establish the relationship, the rate law, that relates concentration to the actual rate of that reaction. The example here is the one that created the ozone hole in the 80s and 90s. So that reaction is written, and then the map just shows you where you have low concentrations of ozone due to the depletion of this molecule O3, which is ozone. So the experimental method is called the method of initial rates, and really it's the simple idea that as long as you measure the concentration of the reactants or the products right at the beginning of the reaction, then it doesn't matter that much about that decay that we saw in previous videos, because all of the things can be related right at that moment in time. And what you can do is systematically change how much or the relative amounts of each of those reactants are present, and then measure that instantaneous rate, and we can start to see the relationship between concentration and the overall rate. And so what I show you here is actual data that were collected that shows under 5 different experimental trials the time zero, the very initial rate that was measured, which is the box way over here to the right, under different concentrations of the 2 reactants that we see in this plot. And so you can see in trial 1, we start with this concentration, 1 times 10 to the minus 6 moles per liter. And with ozone, we have 3 times that, and we have this corresponding rate. What's useful, the way to interpret this, is to look and find first areas in the data where the concentration of one of the reactants is held constant. So notice between trial 1 and 2, NO concentration is fixed, doesn't change. But if we look correspondingly at ozone concentration, those concentrations doubled. And so what we can do is use these 2 pieces of data to compare to figure out what the overall order is with respect to ozone. So we know that when NO is fixed and ozone doubles, what happens to these 2 values? Well, if you look at that, you do that with math, it turns out that this number doubles to create this number. So make sure you convince yourself that's true. So in other words, when ozone concentration doubles, the rate doubles, which means that's a 1-to-1 or linear relationship, which would mean the order with respect to ozone would be 1. So we can write this up as rate is equal to some rate constant times NO concentration with an unknown exponent there. We don't know the order yet. Ozone, but for the ozone, we just determined that to be 1. So at this point, pause the video, see if you can see the same logic here, but find 2 trials where ozone is fixed in concentration, but NO changes, and see what happens to the rate to see if you can deduce what the reaction order with respect to NO is. So conveniently, the way this table is set up, if you look at trials 3 and 4, ozone concentration is fixed, and conveniently NO concentration doubles. So what happens when we double that concentration and ozone remains fixed? Well, these numbers double, the rate doubles, and so we can say that this order is also first. And so we could say that the reaction rate is first order in NO, and first order in ozone, and second order overall. Sometimes when you're looking at methods of initial rates and you say, well, this one doubles and this one clearly doubles, it's obvious, and sometimes it's less obvious when the factors aren't simply a factor of 2 or 3. And so in that case, rather than doing it in your head, you can write it out explicitly, just algebraically. So really you're just writing out 2 different rate expressions or rate laws for each of the trials. So here we have rate 3, so that's for trial 3, and then we have the rate law for trial 4 here. The rate laws are the same and the exponents are the same because we know the rate law has to be the same for both of these things. We just don't know it. And you can put any arbitrary variable here. I just put x and y. And k is, again, the rate constant. Since that is a constant, we can cancel it out because they would cancel when you divide. So I can rewrite this green expression now using the actual values from the experimental data here. So here's the rate of trial 3, that's just this number. Here's the rate of trial 4, that's this number. So I'm just substituting in these values. And then I'm popping in the actual concentrations for the expression that's written up here. We don't know x and y yet, of course, so I leave those as x and y. But notice that because this is not changing, we can cancel that out. That simplifies our expression considerably. So I can just punch these numbers into a calculator. I get 0.5, which is the same as the mental math we did before, and same with these two numbers. They're both raised to the same exponent, so that just becomes 0.5 equals 0.5 to the x. Of course, this is a pretty easy one we can solve in our head. We know that x has got to be 1 here, but let's say that these weren't. How would you actually solve this? Well, to solve this exponent here, then we need to take log of both sides. So that looks like this, so log 0.5 equals log 0.5 to the x. If you remember your log rules, that when you take a log of something to the exponent, then the exponent comes out in front. So I just rewrote this as x log 0.5. And the way that's nice is now I can just divide those two to simplify. So I would just divide this log 0.5 onto the left side of the expression to get x by itself. And of course that is x equals 1, which we already knew, but this is an explicit way to solve this if and when you'd like to do that, if the numbers aren't simple. One more quick thing to do, I'm not going to write this out because it's quite intuitive, but sometimes it'll be useful to actually solve for the kinetic rate constant k here, and that should be doable at any one of these points because you have all of the variables. If I shift this over a little bit, and I have this rate expression that we've already derived. Once you've figured out what the orders are, then this thing is fully defined. So you go to one of these trials, it doesn't matter which one because they're all going to be the same. The rate constant will be the same for each one. You pop in a value for rate here, you pop in a value for NO concentration here, to the first power, ozone concentration to the first power, you solve for K, that gives you the rate constant. So I won't solve this, but I will make a comment on the units of the rate constant. So the units are actually dependent upon the order of the reaction. Why is that? Well, the units for rate are just going to be the amount per unit time. So it could be moles per second as an example. And so that's sort of fixed. But now let's look at the units for these other things. So the concentration is going to be moles per liter for NO, and it's going to be moles per liter for ozone. And these both, in this case, are going to be raised to the first power. Remember, the units are going to be treated the same way as any of the values in that expression. So without the constant, you can see that our units don't add up. The units on the left are moles per second, and the units on the right are moles times moles, which is the same as moles squared, over liters squared. So how do we get these two sides to match? Well, that is what constants are in all of science. They're constants of proportionality. They help our unit. So that means you need to figure out what the units are to make sure that these two sides are the same. So see if you can algebraically work that out. So if we look at this and just think about it algebraically, I don't want any liters on this side. They're completely gone. So that means I need my constant to have units with liters squared up in the numerator. So I just wrote that up at the top. So I'm going to cross that out. That goes away. Now if I look at this, I'm left with moles squared. And I need this to just be moles. So I'm going to put one of those moles down here. That's going to get rid of one of my moles. And I need the seconds here, so that's where I added the second. And so K, the units in a second order reaction, which I know because there's these two exponents here, are going to have units of liters squared per mole second. So see if you can figure out, if I have a first order rate law, that is say K NO, figure out what the units of K are and see if they're the same or different. I'll give you a hint, they should be different, and see if you can figure out what they are.